Thanks for the introduction and thanks for inviting me to speak at the Journal Club. And yeah, so today I want to talk to you guys about fast forwarding quantum evolution. And it's let me see if I can full screen. Okay, yeah. So it's a project that I did with Rolando Soma and Burak Zahinoglu, who are at Los Alamos. And this is the archive reference for the work, if you're interested in checking out the paper. Yeah, we're talking about quantum simulation. And oh, by the way, so if you guys have any questions, yeah, please just interrupt me and ask so that we can all be on the same page. Yeah, so the work is on quantum simulation. And quantum simulation, it's an important problem from both practical and foundational points of view. On the practical side, it's important to be able to test different models and to predict behaviors of different systems in physics, chemistry, or biology without actually having to build the system itself. And its quantum simulation is also a potential application of near-term devices, which people are interested in. On the more theoretical side, aside from being an interesting problem in its own right, quantum simulation can also be used as certain subroutines in other quantum algorithms. So for example, the HHL algorithm for solving linear systems uses quantum simulation as a subroutine, and also quantum phase estimation is also using it as a subroutine, which I will talk a bit about actually later in the talk. So if we want to simulate a quantum system using a classical computer, then it's not really going to be tractable because, for example, if we use the most naive way of just encoding the quantum state as a vector, the vector is going to be exponentially sized because the dimension of the Hilbert space is growing exponentially with the system size. So that's not classically feasible. And instead, we would want to use a quantum computer to do the simulation itself. So here I have a schematic for how we might accomplish this task. We start with a quantum system that represents a physical system that we're interested in. Then we map the degrees of freedom of that physical system to the degrees of freedom of a quantum computer, let's say a qubit quantum computer. And the initial state is going to be some vector, which is psi for that qubit quantum computer. Then we want to implement the time evolution operator of the system, which is given by e to the minus iht, where h is the Hamiltonian that is mapped to the quantum computer. So typically we would decompose this unitary into some elementary gates that we can easily implement on the quantum computer. And finally, we would make a measurement at the end, which would give some result m. And afterwards, we can do some classical post-processing to determine the quantity that we're interested in. For example, the expectation value of some observable. Now, for a simulation like this, we're interested in how the complexity of the simulation scales with different parameters of the system. So for example, we would want to see how it scales with the system size, n, the evolution time, t, and how accurate we want the simulation to be, so the error epsilon. And for this talk, I want to focus in particular on the scaling with the evolution time t. Now, generic simulation algorithms typically have scaling that is going to be at least linear in t. And there's some no fast forwarding results that show that sublinear scaling is not possible. So here I'm just listing a few of these results. In 2007, Berry, Ahukas, Cleve, and Sanders showed a no fast forwarding result in the query model. And in this model, the Hamiltonian is, let's say, a sparse Hamiltonian, and it's we only have black box access to the matrix elements of that Hamiltonian, and the complexity is counted by the number of queries that we do. So the number of queries is going to be at least linear in t in the worst case. So that's a no fast forwarding result that they proved. And in 2017, there was a result by Atiyah and Aharonov, and there they proved no fast forwarding in the gate-based model, where the complexity is measured by the number of 2-qubit gates. And that's also the model that we're going to be interested in our work. So there they proved no exponential fast forwarding, which means that if you want to simulate for an exponential amount of time, then you cannot use just a polynomial number of gates. And this result is also under the assumption that BQP is not equal to P space, which is a conjecture that is widely believed to be true in complexity theory. Then in 2018, there was another result by Ha, Hastings, Kothari, and Lowe that showed no fast forwarding in the gate-based model of any kind, so not just exponential. But there they consider time-dependent local Hamiltonians as well. So the class of Hamiltonians that the generic simulation algorithm is required to simulate is more general because it is allowed to be time-dependent. So all of these results are kind of no-go theorems saying that we can't do generic simulation using sublinear scaling in T. But that doesn't mean that there can't be particular Hamiltonians that we are able to achieve sublinear scaling. So, and there are some easy examples of this as well. I'm just listing a few here. The first one that I have is efficiently diagonalizable Hamiltonians. And this means that H is written as UD U dagger, where D is a diagonal matrix. And if U, the diagonalizing unitary, can be implemented efficiently, say in polynomial time, and often like the exponential of a diagonal matrix is also a diagonal unitary, and that can be implemented efficiently, then this whole thing can actually be fast forward as well because of the diagonalization. Another case where we can fast forward is if the Hamiltonian has an integer spectra. So all the eigenvalues are integers. And in this case, the evolution of the system is actually periodic. So if we want to simulate the system for a large amount of time t, then we can just take t mod 2 pi and it will give the same result. And then we can do the simulation for this constant time using any traditional method, for example, Schroederization. And lastly, there's also the case of commuting local Hamiltonians, and this was also considered by Atiyah and Aharonov. So if the Hamiltonian is the sum of some commuting local terms, then the exponential of the Hamiltonian is just going to be the product of the exponentials of these local terms. And since each of these things acts on only locally, then it can be implemented with constant cost. So the entire simulation is very efficient, even though the t can be very large. So all of these are examples of fast forwarding. Now, for generic simulation algorithms, a lot of the times what they do is you divide up the entire time into some small time slices like delta t, and then you have some way of doing the simulation for delta t, and then you combine all of these together to do the full simulation. But if you use such an approach, then it's going to have at least linear scaling in t, because that's like the number of time slices that you have. So in order to do fast forwarding, like we have to exploit some extra structure in the Hamiltonian to take a shortcut and get around this dividing up the times into small slices. And that's what I'll do for the rest of the talk. Okay, so are there any questions about any of the things that I've said so far?
I have a question. So you mentioned that, like, I mean, at the end of the day, the end goal is to basically measure some observable expectation value, right? So,
yes.
yeah, so, yeah, and often you have some initial state in mind, I mean, for which you want to, let's say, evolve. So,
yes.
like, is it possible that for all possible initial states and, like all possible observables, fast forwarding is not possible? But let's say at the support of some initial states And for some observables, maybe the answer that you are getting, so all these no-go results that people have come up with, maybe, it works for some observables of interest. Let's say some, observable which is of relevant to practical setting. And yeah, so any thoughts about that?
Yeah, that's true. So the no-go results are typically for the full Hilbert space. And actually, we do consider some examples where we actually restrict to a particular subspace, and I'll actually talk about that later as well. So yeah, it's true that if you restrict to a subspace, it might be possible to do fast forwarding, whereas if you had done it for the whole space, then it might not be possible. Yeah, so that's right. Okay, good. So here is just the outline for the rest of the talk. So I'm going to provide some rigorous definitions for what I mean by fast forwarding. Then using those definitions, I will show you some classes of Hamiltonians that can be fast forwarded. So the first one is the block diagonalizable Hamiltonians. And within this class, we consider the permutation-invariant Hamiltonians. And I'll show you the circuit for fast forwarding this. We also consider frustration-free Hamiltonians. And for these Hamiltonians, we restrict to a subspace of low energy. And within this subspace, we're able to achieve quadratic fast forwarding. So type of polynomial fast forwarding. And lastly, if we have time, then I'll also talk about Lie-algebra diagonalization. And using this method, we can get systems like the quadratic fermionic and bosonic systems. And finally, I'll give some concluding remarks. Okay, so the definition of fast forwarding. So first, let's talk about the complexity of doing a certain simulation. And let's consider a sequence of Hamiltonians, Hn, that act on some Hilbert spaces, script Hn. And let's say that we have some circuits Vn of t. Then we're going to say that these circuits simulate the sequence of Hamiltonians with parameters t of n, epsilon, and g of n. If the quantum complexity is at most g of n, which means the number of 2 cubic gates, for example, is at most g of n, the accuracy is at least better than epsilon, which means that it approximates the ideal evolution, e to the minus ith, with accuracy better than epsilon. And the simulation time, so we can do the simulation up to time capital T of n. And to be a bit more general, we can also restrict our initial state to be in some subspace Sn. Okay, so you might be wondering why we don't just fix a particular Hamiltonian and talk about the time scaling, since that's what we're interested in. But the problem is that if we fix the Hamiltonian, then the system size is also fixed. So if we want to do the evolution for very long amounts of time, then we can always, for example, exactly diagonalize the Hamiltonian. And in that case, we'll use approximately 4 to the n gates. But if t is going to very long times, then 4 to the n is also a constant because we fixed n. So that wouldn't really make sense. And that's why.
Which norm you are using? Sorry to interrupt. Which norm is there?
Yeah, so this norm is well, in this case, it will just be the vector norm, because it's the operator acting on some vector.
Yeah, so, okay. Some L1 norm something.
Yeah, I mean, all the norms are equivalent because we're dealing with
up to some constants, right? Yeah.
Yeah, I mean, you can also talk about the operator itself, and then you can use the operator norm for that. Right, so we consider a sequence of Hamiltonians, so that way, when we consider asymptotics in t, then we can actually just let n go to infinity, and then we can consider longer and longer times. So everything is dependent on the system size n. Okay, so when we have the simulation parameters, we can talk about the no fast forwarding line. And the no fast forwarding line is with respect to a certain class of Hamiltonians, Cn. And usually we take Cn to be pretty general. For example, all normalized local, k-local Hamiltonians. And the no fast forwarding line is the worst case complexity that is needed to simulate any Hamiltonian in this class. Okay, so we maximize over all Hamiltonians in this class and the number of gates that we need to do the simulation. And the minimization here just means that we take the optimal circuit to do the simulation for that particular Hamiltonian, but we maximize over all Hamiltonians. Okay, so if we have a Hamiltonian and then we have a circuit that can simulate that Hamiltonian with that's like where the complexity scales asymptotically better than the worst case, so G of n is little o of L of n, that's when we say that we have fast forwarding because it can do better than the general case. Like any generic simulation algorithms would not be able to beat L of n, but we are able to simulate better than L of n for that particular Hamiltonian, and that's why we call it fast forwarding. Okay, so does that make sense to everyone? Basically just when we can beat the general case. Yeah, usually this L of n cannot be found like precisely because we don't know what the optimal quantum circuit is to simulate some Hamiltonian. So the best we can do is get lower bounds of L of n, and that's what the no fast forwarding theorems do. And if you if G of n is better than the lower bound, then we definitely have fast forwarding. Okay, so for this talk, we always assume that the lower bound is going to be something like a polynomial in n times t of n. So it's going to be scaling linearly with t. So if we can beat that, then we have fast forwarding.
So this is the first time we're talking about subspaces here, right? I guess in the earlier definition, subspace was absent, right? Or no, it's here in psi n, right? Yeah.
Okay. Yeah. So psi n would be restricted to subspace.
I see. Okay. Yeah. Okay. Mm-hmm.
Okay, good. So now let me give the first example of fast forwarding, and it's for block diagonalizable Hamiltonians. And this is a pretty straightforward generalization of the diagonalizable case. So we have a Hamiltonian H that is acting on script H. And let's say that the Hilbert space can be decomposed into invariant subspaces of the Hamiltonian. And so then H is going to be decomposed as a direct sum of H restricted to these subspaces. Then what we want to do is find a unitary that block diagonalizes the Hamiltonian. So what I mean is that we start with, we can possibly have an ancillary register as well. But when we conjugate by U, then it's going to decompose into these blocks, and where mu is the block label. And the block label is has its own separate ancillary register. Then within the block diagonal basis, we want to implement the time evolution operator of each block. So that's going to be U prime of t, which is just the sum over all the block labels of the U mu of t, which is e to the minus I t h prime now, the new Hamiltonian, restricted to that block. So this is the circuit that we use. So first we apply U, then we apply the evolution operator in the diagonal basis, and then we undo the U. And we can fast forward if all of these components can be implemented efficiently. So for example, U is polynomial in n, and the U mu of t is also, let's say, scaling logarithmically with t. And sometimes this part here might have some trouble because there could be an exponential number of blocks mu. So it's not, it's not immediately clear how we might implement this conditional operation. But one way that we could do it is, for example, if we have a classical algorithm that can calculate u mu of t. Okay, so this, in the diagonalizable case, this means that we're able to efficiently calculate the eigenvalues of the Hamiltonian. And when this is possible, we can use a reversible classical, a reversible implementation of C, and then that will translate to a quantum circuit as well. And then we can add another ancillary register, and then applying that quantum circuit now, we have an encoding of the gates that are needed to implement u mu of t. Based on that encoding, then we do a conditional operation and apply those gates on the data qubits. Okay, and afterwards we undo the classical computation. So this way, it gets all of the mu's at once, because this is a quantum circuit and we can do the mu's in parallel. So this will work even if there's an exponential number of mu's, as long as we can calculate the circuit for each one. Okay, and let me focus now on a specific case of block diagonalization, which is the case for permutation-invariant Hamiltonians. So let's consider a Hamiltonian H that's acting on a Hilbert space, which is a tensor product of n d-dimensional spins. And we assume that H is permutation-invariant, which means that it commutes with all permutation operators P sigma, where P sigma acts on this Hilbert space by permuting the tensor factors. And sigma is an element of the...
Sorry, can you go to previous slide?
Oh, sure.
Yeah. So the control unitary that you have, is it like a multi-control? Like, I mean, like it acts on the entire register, the control qubit. I mean,
yeah, it would depend on like exactly how you do the encoding. There might be some overhead with it, but it's essentially just saying that, you know, if the encoding saying like what the first gate is going to be, and then you do base control on that, and then you do the actual gate on the data qubit, and then
yeah,
you do
so
it for the...
I'm thinking about the case where, you know, like this the block decomposition. I mean, that's possible there, you know, like let's say there either like, you know, exponentially many blocks. So does the number of blocks you have has any effect on the number of control qubits you require for the implementation of this control unitary?
No, it shouldn't affect the encoding, because I mean, as long as for each block, like the circuit that you need to implement that block doesn't have an exponential number of gates. So let's say it only has like a logarithmic number of gates, then you don't need very many ancillary registers here, because you're only encoding the gates that you need, not like which block you're coming from.
I see. Okay, thanks. Mm-hmm.
Yeah, so there's some detail here in this gate that I haven't explicitly written out.
I'm just wondering, you know, some complexity might be hidden there.
Right. I mean, yeah. So I think like as long as the circuit itself, like u mu of t, is not does not decompose into too many 2 qubit gates, then the number of ancillary registers is also not too large.
Mm-hmm, mm-hmm.
Okay, good. So yeah, we're talking about the permutation-invariant Hamiltonians. And right, so one characterization of the permutation-invariant Hamiltonians is that it's an element of the universal enveloping algebra, which means that the terms of H are going to be products of generalized angular momentum operators. And what I mean here is that it's going to be the sum of just A acting on each component separately. So these things are, you can see, are permutation invariant. One example of such a Hamiltonian is the Lipkin-Meshkov-Glick model. And this is a model introduced, I think, in the 1960s, but it was used to study some phase transitions in nuclear physics for an exactly solvable model. And it's usually written in terms of fermionic operators, but you can do a transform to get to write it in terms of angular momentum operators, and H will be written in this form. And because the angular momentum operators are permutation invariant, then the whole Hamiltonian is going to be permutation invariant as well. So our method is going to apply to this particular model as well. Now, the main ingredient that we use to simulate permutation-invariant Hamiltonians is the Schur-Weil duality. So we break down the Hilbert space into as a representation of the unitary group and the symmetric group. The unitary group acts on this space by acting with the same unitary on all the tensor factors, and the symmetric group permutes the tensor factors. So the entire Hilbert space is going to decompose into irreducible representations. And it's going to be labeled by lambda, which is a partition of n into at most d parts, which is not too important. But the important part is that it's going to be some irrep of the unitary group tensor with an irrep of the symmetric group. The fact that H is permutation invariant means that when we decompose it in this way, H does not act on the P lambda part, does not act on the symmetric group representation. So it's only affecting the unitary part. Okay. And one simple example of Schur-Weil duality is the tensor product of two spin 1/2s. So it's decomposing into the triplet and the singlet, where the triplet is the spin 1 representation, and the singlet is the spin 0 representation for the unitary group. And for the symmetric group, this is the trivial representation, and this one is the sign representation. Okay, and this is the circuit that we use to do the simulation. So Bacon, Trong, and Harrow introduced a Schur transform unitary. And what the Schur transform unitary does is basically break down the Hilbert space according to the Schur-Weil duality that we just talked about. So we start with a state x in the computational basis. Then when we apply this unitary, it's going to be a sum of like lambda, p, and q, where lambda is a block label, p is the symmetric group representation, and q is the unitary group representation. So basically exactly according to that decomposition that we talked about. Once we decompose, once we transform into the Schur basis, we can apply the block evolution. Okay, so because this is the block, the Hamiltonian is now block diagonal in this basis. So we control on the label lambda, and we apply the unitary on the data qubits in the unitary group representation. And after we do the block evolution, then we transform back into the computational basis. Now let's look at the complexity of this simulation. So the Schur transform the complexity of this unitary was analyzed in this paper. And there it was found to be polynomial in n. So that's no problem there. And if we look at this middle gate, we can look at what the size of the Q register is. And it turns out that in the setup that we have, the maximum dimension of the unitary representation is at most n to the d squared, which is polynomial in n because we're fixing d. And we can also say that this register lambda is also a polynomial in n, although that's not so important because we can always use the method that I described previously. So this means that the entire circuit has complexity that is polynomial in n, but we can let t be exponential. So this allows for exponential fast forwarding. Now, the entire Hilbert space has an exponential dimension, but the point is that when we go to the Schur basis, most of those degrees of freedom have gone into the symmetric group representation. And the fact that H is permutation invariant means that we don't touch this register. So the only parts that do matter are only have polynomial dimension, which is where we obtain the savings here, because each block is polynomially sized. Okay, does anyone have questions about permutation-invariant Hamiltonians? Okay.
Bailey, could you say a little bit about the A1 prime and A2 prime based on your Young's diagram?
Yeah, so A1 prime and A2 prime are kind of like ancillary registers, because they're only because the actual block is in the unitary group representation. But yeah, if you follow like the Schur-Weil duality, you can figure out like exactly how like these registers will behave. So I don't know if that completely answered your question, but like, which part about the Young diagram were you interested in?
No, I mean, like, basically you are decomposing into some unitary and symmetric subspace.
Yeah, that's right. So lambda is like the Young diagram.
Okay, so you take one, because your Young's diagram is decomposing to a permutation subspace together with a symmetric.
Yeah, yeah.
Okay, fine. Thanks.
Okay, cool. So now let me talk a bit about frustration-free Hamiltonians. We're considering a Hamiltonian that's the sum of hx, where this term acts on a subset x of the full lattice lambda. And there's going to be L non-zero terms, which are all positive, and they have bounded norm. The fact that the Hamiltonian is frustration-free means that the lowest eigenvalue of h is 0. The main technique that we use for fast-forwarding the frustration-free Hamiltonians is a spectral gap amplification, which means that we can construct a new Hamiltonian h prime that essentially acts as the square root of the original Hamiltonian. So when we construct h prime in this way, and we act twice with h prime on some state phi, then it's the same as if we had acted once with the original Hamiltonian. And that's why I say that h prime is like the square root. Because of this, the eigenvalues of h prime are going to be 0 and plus or minus the square roots of the original eigenvalues of h. Then, when we restrict to a low energy subspace, the eigenvalues of h prime are going to be more spread out than the eigenvalues of h. So in particular, if we want to estimate an eigenvalue with accuracy epsilon over t for the original Hamiltonian, then it suffices to do an estimate with slightly worse accuracy around the square root of the new Hamiltonian h prime. Now, there's also a correspondence between the ability to fast forward and the ability to make very efficient energy measurements. And let me just describe that a bit. So let's say that we're able to fast forward a Hamiltonian or just simulate a Hamiltonian efficiently. Then this is the quantum phase estimation algorithm. And it essentially, in the middle part, it involves some control operations of gates that are essentially simulating the Hamiltonian. So if you do the analysis for a circuit like this, then it can be shown that if we're able to do simulation for time up to t, then we get an energy measurement accuracy of around 1 over t. Conversely, suppose that we're able to do efficient energy measurements. This means that if we start with an eigenstate, then we apply some unitary, and then we can get an encoding of the energy in a separate register. Then what we can do is just apply a phase onto this new register, e to the minus ite. And then if we undo the energy measurement circuit, we basically have put the phase onto the eigenstate. Okay. So if we have a superposition of eigenstates, then it's also going to work the same way, and we will achieve simulation of the Hamiltonian. And the analysis for this one can show that if we do energy measurement with accuracy delta E, then we can get simulation for time t up to 1 over delta E. Okay, if we put together all of these facts that I kind of just stated, we can prove fast forwarding of frustration-free Hamiltonians. And here is the theorem statement. So we have a Hamiltonian that is a sum of L terms and is frustration-free. And we also restrict our initial state to be in a subspace of low energy. So the energy cutoff delta is scaling as 1 over t, where t is the maximum simulation time that we're interested in. If this is the case, then the Hamiltonian can be simulated with these parameters. So the number of gates is going to be scaling as n L squared times the square root of t. So the square root of t here means that we have quadratic fast forwarding. And you may already see how the proof of this might go based on the previous facts, but I'll just give an outline. So first, we perform an energy measurement for the new Hamiltonian, the square root Hamiltonian, with slightly worse accuracy. That's around the square root of the actual accuracy that we need. And this can be done by simulating h prime up to time 1 over delta. After we do this, we get an estimate of lambda, the eigenvalues of the Hamiltonian we're interested in, with the accuracy epsilon over 2t. And I mean, this one we can just square lambda j prime. After we do this, we implement the phase, and then we undo the energy measurement. And at the end of the day, we will get simulation of the original Hamiltonian with the desired accuracy.
Bailey, how does simulating it for up to time 1 over delta give you the energy measurement?
Sorry, I didn't quite catch that. What you said?
How do you perform the energy measurement in the first step?
The first step.
Yeah.
Yeah, so we use this quantum phase estimation algorithm, where instead of using h, we use h prime.
Okay. Thank you.
So like we use some generic simulation algorithm that scales almost like basically linear scaling in t, for example.
Thank you.
Cool. Okay, do I have time to talk about the next part?
Sure. I think it's cool.
Okay. Well, yeah, let me talk about Lie-algebra diagonalization then. So I think it's best illustrated with an example. And the Lie-algebra diagonalization is very similar to Jacobi eigenvalue algorithm, which is a classical algorithm. So let's say that we want to diagonalize a Hermitian matrix like this. What we can do is identify the off-diagonal element with the largest norm. So in this case, it will be the 7. Then we apply a Givens rotation to eliminate this entry. So basically we conjugate by a matrix like this, acting only on the first and third rows and columns, which will eliminate the 7. Then we can repeat this process. So look at the new matrix that we have and identify the largest off-diagonal element, which is the minus 6.19, apply a Givens rotation and get rid of that entry. So this time it'll be acting on the second and third rows and columns. and we can zero out that entry. And when we do this, it's possible that the original 0 that we had is going to be non-zero now, so it's going to be messed up. But no, that's okay. So like we just keep repeating this procedure. So we identify the largest off-diagonal element, and we apply the Gibbons rotation to eliminate it. And if you do this over and over again, it can be shown that the matrix is going to converge to a diagonal matrix. So that actually all of the off-diagonal elements are converging to 0, and it's converging to 0 exponentially. And when we do Lie-algebra diagonalization, it's just a generalization of this algorithm, but for Lie algebras. So the actual statement is going to be a bit technical, but the Hamiltonian H is an element, we assume that's an element of a real compact semi-simple Lie algebra with small dimension. Then we use a Cartan-Weil basis decomposition, which means that we can decompose G into the sums of certain subspaces. The first subspace is H, which is the Cartan subalgebra. And the Cartan subalgebra is a maximal commuting set of elements in H. So this is playing the role of the diagonal matrices. And we want to conjugate H by some unitary to get it into the Cartan subalgebra. And it's also the direct sum of some root spaces G alpha. And these root spaces, basically, because the Lie algebra is compact, it's going to generate copies of SU2, and it's going to be spanned by some elements like X alpha, Y alpha in the root space G alpha, but also Z alpha, which is diagonal. And these elements will satisfy the usual SU2 commutation relations. So this is the Cartan-Weil basis decomposition. And the procedure that we have for diagonalizing is as follows. So we start with the Hamiltonian H, and at each step, we decompose Hj according to the Cartan-Weil basis decomposition. So it's going to be the sum of a diagonal part and some off-diagonal terms. So, and the off-diagonal terms are is a linear combination of the X alphas and Y alphas. At each step, we choose the alpha j such that the coefficient a squared plus b squared is maximal. So we choose, basically this is playing the part of choosing the off-diagonal off-diagonal element with the largest norm. Then within that copy of SU2, we diagonalize it. So we eliminate these two coefficients by applying an SU2 rotation, which is the exponential of some linear combination of X alpha and Y alpha. So after we apply this rotation, then that particular A and B will be 0. And then we repeat this procedure. Now, if we do this, then it was shown by Wilberger in the 1990s, I think, that the element or the Hamiltonian is going to converge to something that is diagonal, and it's converging exponentially with the space. L is the number of positive roots, which is at most half the dimension of the Lie algebra. And that's why we want the dimension to be small, so that this is converging fast. If we rearrange this expression, then we can show this corollary, which means that if we want to reduce the off-diagonal norm by a factor of epsilon, then we just need to run like order log epsilon number of iterations of the algorithm. Okay, so once we diagonalize, then we can, that will basically allow us to simulate the Hamiltonian, because then it'll just be a diagonal part. So the way that we do this is that we apply the V's, which were the SU2 rotations. Then we exponentiate the element of the Cartan subalgebra. So that in principle should be something that is easy to do because it is diagonal. And then we undo this V's. And when we analyze the circuit, then we find that we can exponentially fast forward if we satisfy these three conditions. So the Lie-algebra has to have small dimension so that we don't have too many of these SU2 rotations. Also, each SU2 rotation should be implementable in polynomial time. And also the diagonal part, when we exponentiate, should be implementable in polynomial time. And lastly, we have this technical condition that the operator norms and the Lie-algebra norms have to be related in some way, because when we showed convergence for that Lie-algebra diagonalization, it was actually in the Lie-algebra norm. But most of the time, like when we do simulation, we're interested in the operator norm. So we have to be able to relate these two norms to each other. But if these three conditions are satisfied, then we can go for an exponential amount of time to obtain exponential fast forwarding. Okay, so that's the general technique. And let me just illustrate some examples using this. So the first one is quadratic fermionic Hamiltonians. And in this case, H is written as a sum of these terms, where the Ci's and Cj's are fermionic creation and annihilation operators, which satisfy the canonical anti-commutation relations here. When we analyze the Lie-algebra generated, it's going to be isomorphic to SO2n. So I say Hermitian terms of H, which means that like we, for example, like pair off the Ci-Cj with the Ci dagger, Cj dagger, so that like all of the terms that we're actually considering are Hermitian. And that way we can generate a real Lie-algebra. And SO2n has dimension that's approximately n squared, so polynomial in n. I don't have all of the analysis here, but if you go through like and start to count the number of gates, then it's going to be, then we can show that it's fast forwarded with these parameters. So as you can see, like we have a log t here, which means that we exponentially fast forward. And also we can consider the quadratic bosonic Hamiltonians. And here I'm going to restrict to the number conserving case, where we only take the Ci dagger Cj terms. And now Ci and Cj are bosonic operators, which satisfy the canonical commutation relations. So when we restrict to the number conserving terms, then the Hermitian terms of H generate a Lie-algebra that's isomorphic to SUN. And that also has polynomial dimension. And then we can do a similar analysis to get that these quadratic bosonic Hamiltonians can also be fast forwarded with the same parameters, scaling with the log t number of gates.
Is there some kind of a classical hardness result known for, you know, like simulating such cases?
I think there's no problem simulating these classically even, because of this like Lie-algebra diagonalization. You can like also classically calculate all of the eigenvalues. You can just diagonalize this classically as well.
Yeah, yeah.
Yeah, but I'm just like illustrating, like giving these examples to illustrate the Lie-algebra diagonalization technique. Like it has already been known before how to simulate these kinds of Hamiltonians. Oh yeah, so here I didn't include the non-number conserving terms. And the reason for that is that if we include those terms, the Lie-algebra that's generated is not going to be compact. So it's some real Lie-algebra, and the complexification is sp2n. but the real Lie-algebra itself is not compact. So in our analysis, like the conversions to a diagonal Hamiltonian is not going to make sense. Like you can't define a suitable norm. And this is not just a technical like thing that we can't solve. It's actually that like for those types of Hamiltonians, you can show that the kinds of like SU2 rotations that you would want to use to diagonalize the Hamiltonians are not sufficient. Like these are basically Bogoliubov transformations. And if you just use those to try to diagonalize, like there are some Hamiltonians that cannot be diagonalized using Bogoliubov transformations when there are non-number conserving terms. So like this method, so you would need to use some other method to simulate those. Okay, so that's the last example that I wanted to discuss. Let me just give some closing remarks. And yeah, so we provided a definition of fast forwarding that is fairly rigorous. And using that, like within that framework, we were able to fast forward certain classes of Hamiltonians. And those included the permutation-invariant Hamiltonians, which is an example of block diagonalization. There was the frustration-free systems, where we did quadratic fast forwarding in a low energy subspace. And we also talked about quadratic fermionic and bosonic systems, which can be diagonalized within a Lie algebra. There are still some open problems that remain. So one of them is to find applications of these techniques that I've described. So for example, like the Lie algebra diagonalization technique is pretty general, right? Like it doesn't just work for quadratic fermionic and bosonic systems. And yeah, so it would be interesting to see if there are other physically relevant systems that could be fast forwarded using that framework. Another direction that that would be interesting to see is if we can characterize systems that can be fast forwarded. There is the characterization in terms of efficient energy measurements, but I'm talking about like if someone just handed you a Hamiltonian and like would you be able to tell if that Hamiltonian could be fast forwarded if there was some easy way to check. I'm not sure this is an easy problem, but it certainly would be interesting to know. And finally, we can also find more general no fast forwarding theorems for different classes of Hamiltonians. Okay, so that's the all I wanted to talk about. Thanks for your attention.
Thanks, Willie, for the very nice talk. So, and now I think we can open the floor for questions if anyone has any.
Hi, Willie. I just have I'm not sure whether this is a simple or hard question, but because we know that there are some classically we have this sort of integrable systems, and then in the quantum, maybe in the quantum computing perspective, we are looking at things from the fast forwarding perspective. I was wondering, do you have any insight whether these two sets are the same, or are there actually classes or Hamiltonians that, for example, cannot be fast forwarded but are actually integrable, or
oh, you're saying like if it can be solved classically as well, like all of the cases. Yeah, I think the frustration-free case would be something that cannot necessarily be solved classically very easily, but like we are able to fast forward at least in a subspace.
Okay. Yeah.
So I don't. Yeah, certainly those two notions seems to be related because a lot of the examples that I gave were related. I mean, like were able to be simulated classically.
Yeah.
It seems like it's not like a one-to-one correspondence.
I see. Thanks.
Yeah.
Just curious, have you tried running any of these algorithms on classical computers? I mean, like, sorry, not classical, on current quantum computers like IBM Q or something like that?
Was the question like whether we tried these algorithms?
Yeah.
No, so we haven't tried a lot of these algorithms on like actual hardware, and I suspect that like like maybe some of these algorithms actually have like large overhead. So for example, like the permutation invariant case, like although everything is polynomial, like we have, for example, here like, you know, n to the d squared dimension, which could be quite large in practice, and so might be kind of like prohibitive on the current architectures.
Hi, Shouzhen. This is Jose Ignacio. Well, actually, the quadratic fermionic fast forwarding was done by Alba Cervera in IBM Cube some years ago.
Okay.
Actually, she won the competition, the first competition of IBM with this algorithm. So it has been done. Okay.
Oh, I see. Okay, yeah. I guess that.
So the unitary is just the Jordan-Wigner transformation, and therefore you diagonalize the system, and you can apply not only the time for fast forwarding, but the same technology serves the purpose of having thermal states. You see, it doesn't matter whether the time is real or imaginary, the same technique applies. And then you can also simulate or create artificially thermal states, which are faithful to the reality.
Right. So I guess, yeah, if you can diagonalize it, then you can also create the thermal states.
Yeah, that's the idea. Anything you can diagonalize, you can do either time evolution or Euclidean time evolution. So both of them are possible, and it was done. Okay.
Oh, okay. Thanks. I didn't know that.
If there are no further questions, then I think we can end the meeting today. So thanks really for coming to talk to us again. Yeah, it was a very good talk. Thank you.
Okay, thanks.